Have you ever wondered how a single engineering mistake can destroy years of work? A small oversight, a tiny miscalculation, or one decision that seemed harmless at the time. Sometimes that's all it takes to turn a massive construction project into a billion-dollar disaster. Every bridge, skyscraper, tunnel, and dam is built on thousands of calculations. Most of them are correct. But when even one critical detail is overlooked, the consequences can be catastrophic. Projects worth millions can fail, lives can be lost, and entire cities can be affected. Throughout history, engineering failures have shocked the world. Bridges have collapsed without warning. Buildings have begun to sink years after completion. And structures once considered engineering marvels have become cautionary tales. Many of these disasters were preventable, yet they still happened. Some failures were caused by poor planning, others by unexpected environmental conditions. And some happened because engineers missed a single critical detail hidden deep within the design. The result? Billions of dollars lost, years of reconstruction, and lessons that changed engineering forever. Today, we're exploring 5 of the most expensive construction mistakes ever made. From collapsing bridges to sinking skyscrapers, these disasters transform the way engineers build the modern world. Let's begin. On the 7th of November 1940, one of America's most ambitious bridges collapsed into the waters below. The disaster was captured on camera and would become one of the most famous engineering failures in history. Just a few months earlier, however, the Tacoma Narrows Bridge was celebrated as a masterpiece of modern engineering. Stretching across Puget Sound in Washington state, the suspension bridge was elegant, efficient, and remarkably affordable to build. Many believed it represented the future of bridge design. At the time, engineers were constantly searching for ways to build longer spans while reducing construction costs. The Tacoma Narrows Bridge appeared to be the perfect solution. Its slender design looked modern and sophisticated, earning admiration from both engineers and the public. But beneath its graceful appearance, a serious problem was already developing. Soon after opening, engineers and local residents noticed something unusual. Even moderate winds caused the bridge deck to move. The roadway twisted, bounced, and swayed in ways that had never been anticipated during the design process. At first, the movement seemed almost amusing. Drivers crossing the bridge reported strange sensations, as if they were traveling across ocean waves rather than a solid structure. Some people even crossed the bridge simply to experience its strange motion for themselves. The bridge's dramatic movement quickly earned it a nickname, Galloping Gertie. As weeks passed, the oscillations became increasingly concerning. Engineers attempted to understand the problem, but the true danger was still not fully understood. Temporary solutions were considered, yet none addressed the root cause of the instability. Then came November 7th. Strong winds swept through the Tacoma Narrows. What had once been a curious engineering oddity suddenly became a disaster unfolding in real time. The bridge began twisting more violently than ever before. Sections of the deck rose and fell dramatically as powerful aerodynamic forces acted on the structure. Witnesses watched in disbelief as the oscillations grew stronger. The bridge seemed to be fighting against itself. Each movement fed the next, creating a destructive cycle that engineers could no longer control. As the bridge continued to twist, the movement became increasingly dramatic. Entire sections of the roadway rose and fell several feet at a time. Steel cables strained under enormous stress while the deck bent in ways its designers had never imagined. Photographers and engineers rushed to document the phenomenon. What they captured would later become some of the most famous footage in engineering history. The bridge no longer behaved like a rigid structure. Instead, it moved almost like a ribbon being shaken by the wind. Each oscillation transferred energy throughout the span, making the motion even more severe. By this point, it was clear that the situation was no longer under control. Emergency crews closed the bridge to traffic, and observers could do little more than watch as the structure continued to deform under the relentless forces of nature. For more than an hour, the bridge endured the combined effects of wind, vibration, and resonance. Eventually, the steel and concrete could take no more. Massive sections of the bridge tore apart and plunged into the water below. Remarkably, no human lives were lost. But the bridge itself was completely destroyed. What had once been celebrated as an engineering achievement had become a cautionary tale for future generations. The collapse of the Tacoma Narrows Bridge transformed the field of engineering. It revealed the critical importance of aerodynamics in bridge design and forced engineers around the world to rethink how large structures interact with wind. More than 80 years later, the lessons learned from Tacoma continue to influence the design of modern bridges. The disaster remains one of the most studied structural failures in history, proving that even the most impressive projects can fail when a critical detail is overlooked. Imagine purchasing a luxury apartment worth millions of dollars, only to discover that the entire building is slowly sinking beneath your feet. In the heart of San Francisco stands Millennium Tower, one of the most recognizable residential skyscrapers in the city. Completed in 2009, the tower quickly became a symbol of luxury living. Rising more than 600 feet above the skyline, it offered stunning views, premium amenities, and some of the most expensive apartments in California. For years, everything appeared normal. But behind the glass facade and luxury interiors, a serious problem was developing below ground. Several years after construction was completed, engineers discovered that the building had begun to sink. Even more concerning, the tower was also starting to lean. At first, the movement seemed minor, but as measurements continued, the numbers became increasingly difficult to ignore. The structure had settled far more than engineers originally expected, and the tilt continued to grow. Residents became concerned. Property values came under pressure. Questions quickly emerged about how such a modern skyscraper could experience a problem of this magnitude. Investigations eventually focused on the building's foundation system. Unlike some neighboring skyscrapers that were anchored directly into bedrock, Millennium Tower relied primarily on dense layers of soil beneath the city. Over time, the tremendous weight of the structure caused additional settlement, contributing to both sinking and leaning. As the years passed, engineers closely monitored every movement of the tower. Specialized instruments were installed to track changes measured in fractions of an inch. What seemed like a small amount of movement could have major implications for a building of this size. The situation soon attracted national attention. News outlets across the United States reported on the sinking skyscraper. Legal disputes followed, while engineers searched for solutions that could stabilize the structure and prevent further movement. Repair plans became increasingly complex. Massive engineering efforts were proposed, including new support systems designed to transfer part of the building's load toward more stable ground conditions. The cost of these projects climbed into the hundreds of millions of dollars. Today, Millennium Tower remains standing and continues to be occupied. But its story serves as a powerful reminder that even the most advanced skyscrapers depend on what lies beneath them. In engineering, the most impressive structure in the world can only be as strong as its foundation. And sometimes, the biggest problems remain hidden until years after construction is complete. In July of 1981, a celebration inside a luxury hotel suddenly turned into one of the deadliest structural failures in American history. The Hyatt Regency Hotel in Kansas City was considered an architectural success. Its massive atrium, elegant design, and suspended walkways made it one of the city's most impressive buildings. Visitors were often amazed by the open interior space and the elevated bridges that crossed above the lobby. On the evening of July 17th, hundreds of people gathered inside the atrium for a popular dance event. Families, friends, and hotel guests filled the lobby, while many others stood on the suspended walkways above to watch the festivities below. Everything appeared normal, but hidden within the structure was a flaw that had gone unnoticed. The walkways were suspended from steel rods connected to the ceiling structure above. The original engineering design called for a continuous rod system that would distribute the loads through the connections. However, during construction, a design modification was introduced. At first glance, the change appeared minor. The revised design used two separate rod connections instead of a single continuous rod. The modification simplified construction and fabrication, but it also created a dangerous consequence. The new configuration effectively doubled the load acting on a critical connection point. The forces that the connection was required to support became significantly greater than originally intended. Unfortunately, this change was not fully evaluated for its structural impact. The walkways remained in service. Guests continued to use them, and the hidden weakness remained undiscovered. As hundreds of people gathered in the atrium that summer evening, the connections supporting the suspended walkways were carrying far more weight than they had been designed to handle. Then disaster struck. Without warning, the connection points began to fail. The fourth-floor walkway suddenly collapsed. Moments later, it crashed onto the second-floor walkway below. The impact caused both structures to fall into the crowded atrium. In a matter of seconds, tons of steel, concrete, and debris came crashing down onto the people gathered beneath. Witnesses described scenes of confusion, panic, and devastation. Music stopped, lights flickered, dust filled the air. Many people initially struggled to understand what had happened. Rescue workers rushed to the scene almost immediately. Firefighters, police officers, medical personnel, and volunteers worked through the night searching for survivors trapped beneath the wreckage. The collapse claimed the lives of 114 people. More than 200 others were injured. It remains one of the deadliest structural failures in United States history. The investigation quickly became one of the most important engineering case studies ever conducted. Experts carefully examined design drawings, fabrication details, construction records, and structural calculations to understand exactly why the walkways had failed. What investigators discovered was deeply troubling. The critical connections supporting the walkways possessed only a fraction of the strength required under certain loading conditions. A design modification that appeared simple on paper had dramatically increased the forces acting on the connection. The disaster demonstrated that structural failures are rarely caused by a single dramatic event. More often, they result from a chain of decisions, assumptions, and overlooked details that gradually create a dangerous situation. In this case, a small change introduced during the construction process ultimately led to catastrophic consequences. Engineers around the world studied the findings closely, recognizing that similar mistakes could occur on countless other projects if proper review procedures were not followed. The tragedy sent shockwaves throughout the engineering community. Professional standards were reviewed. Design review procedures were strengthened. Engineering ethics became an even greater focus within the profession. The collapse served as a painful reminder that even a seemingly small change can have catastrophic consequences when structural safety is involved. Today, the Hyatt Regency walkway collapse is studied by engineering students around the world, not because of the size of the structure, not because of its complexity, but because it demonstrated how a single overlooked detail can lead to unimaginable loss. More than 4 decades later, the collapse continues to be discussed in universities, engineering conferences, and professional training programs. It serves as a powerful reminder that public safety depends on the accuracy of every calculation and the integrity of every design decision. The structures engineers create may stand for decades, but the consequences of an error can last even longer. The Hyatt Regency disaster remains a lasting symbol of why engineering responsibility extends far beyond the drawing board. The disaster remains one of the most important lessons ever taught in structural engineering, a lesson written not in textbooks, but in lives lost. A reminder that every calculation, every connection, and every design decision matters. The disasters we've explored today happened in different cities, different decades, and under very different circumstances. One involved a suspension bridge that became a symbol of engineering failure. Another involved a luxury skyscraper that slowly began sinking beneath the skyline of San Francisco. And another resulted in one of the deadliest structural collapses in modern American history. At first glance, these stories appear completely unrelated. Different engineers, different projects, different challenges, different environments. Yet when investigators examined what went wrong, a common pattern emerged. In every case, a critical detail was either underestimated, misunderstood, or overlooked entirely. The Tacoma Narrows Bridge showed engineers that structures do not simply resist gravity. They must also interact safely with wind, vibration, and the forces of nature. Millennium Tower reminded the world that even the most impressive skyscrapers are only as reliable as the foundation supporting them. The Hyatt Regency disaster demonstrated how a seemingly small design change can produce catastrophic consequences when structural safety is involved. These failures were expensive. Some cost millions. Others cost hundreds of millions. And some cost something far more valuable than money: human lives. But history remembers these disasters not only because of the damage they caused, it remembers them because of the lessons they left behind. Every major engineering failure changes the profession. Building codes evolve. Design standards improve. Inspection procedures become more rigorous. Engineers learn new ways to identify risks before they become tragedies. Many of the safety requirements that exist today were developed because earlier generations paid the price for mistakes. In that sense, every failure becomes a lesson for the future. Every investigation becomes an opportunity to improve. And every disaster contributes to safer structures for the generations that follow. Most people never think about the engineering that surrounds them. They cross bridges without considering the calculations behind them. They enter skyscrapers without thinking about foundations hidden deep underground. They walk through buildings without noticing the countless structural elements working silently in the background. When engineering succeeds, it often becomes invisible. But when engineering fails, the consequences can be impossible to ignore. That is why every calculation matters. Every inspection matters. Every connection matters. And every design decision matters. Because the structures engineers create may stand for decades, but the consequences of a mistake can last much longer. Thank you for watching. If you enjoyed this video, be sure to subscribe for more engineering stories, construction failures, mega projects, and fascinating lessons from the world of civil engineering. And remember, sometimes the smallest oversight can change history.